We're in chapter 9.4, and this is going to be called the z-test for hypothesis for the proportion. So we're looking at proportion data, which means we have no means or standard deviations. All we have would be the number of observations with a given characteristic and the sample size. And we have one population here. So here's the example. This is example 9.6, which is found on page 310, 311. An audit reported that McDonald's had a drive-through service time of 188.83 seconds, and it also filed 90.9% of its drive-through orders correctly. Suppose McDonald's begins a quality improvement effort to ensure that orders at the drive-through are filled correctly. The business problem is defined as determining whether the new process can increase, that's a key word, increase the percentage of orders filed correctly. So data are collected from a sample of 400 orders using the new process. The results found that 378 orders were filled correctly, and at the 0.01 level of significance, can you conclude the new process has increased the proportion of orders filled correctly? So we're going to go through our 6 steps here and walk you through that process. Step 1, state the null and alternative. The alternative is the proportion is greater than 0.909, and the population proportion of orders filled correctly is greater than 90.9%. That's what we're trying to prove. The null hypothesis says the proportion is less than or equal to 90.9. So that means really that the new process hasn't helped us any. We're not any faster or better than we were before in terms of percentage of orders being filled correctly. And this is what my Excel output looks like. If I use Excel, it gives me a z-test of hypothesis for the proportion. So it's a single sample z-test for proportion. And so we think that pi equals 0.909. So that's what we put in there at the first step. The level of significance, according to the problem, was 0.01. So we have to put that in there. Number of items of interest, 378. And the sample size is 400. Okay, so here are the numbers that we'll be using then after a while, and it tells us to reject the null. So let's see how we got to that point. Step 2, choose the level of significance, which was given to us as 0.01, and the sample size, which is 400. Now we want to figure out what kind of test are we going to use for this problem and what kind of sampling distribution is appropriate. We want to use an upper tail test because, if you remember back on the earlier slide, it said we want to conclude that the new process has increased the proportion of orders filled correctly. So increased tells me it's going to be an upper tail test. Okay, so we go over here and notice when we put in our Excel, if we did run it with phstat, it'd be an upper tail critical value. So that's reflected in those results. So we want an upper tail, one sample, z-test for the proportion, and we're assuming a random, normally distributed sample where n equals 400. Because we've got a large sample, 400, it's not likely we're going to have any problem with our test for normality because we take 400 times, this would be 22 over 400. So 22 over 400 would give us our percentage. That is greater than 5, and so that's why we know that we can use this test. So we have to have a normally distributed sample here, which we have a large sample of 400, so we should be good. Step 4 is the critical value, the upper tail critical value. We can find that in our table, or we can find it using phstat. And it says here it's 2.3263. If you use the table, it'd be slightly different. It'd be 2.33 is what you'd find in the Z table, and that would be based on an alpha level of 0.01 and an upper tail test. Step 5, we use the formula, which says z-stat is equal to p minus pi over square root of pi times 1 minus pi over n, where pi refers to the population proportion, p is the sample proportion. To find the sample proportion, I just take x over n, 378 over 400, which is 0.945, and that's what I had as my sample percentage, 94.5. I plug that into my formula here, that's p, this is pi, square root of pi times 1 minus pi over n. And so then I solve and I get the z statistic for step 5 is going to be 2.5034. We can also find that by using our phstat result for the t-stat, and that was 2.5034. So here's my calculated value. My critical value is 2.33 or around that. And so therefore, because my calculated value in step 5 is greater than my critical value in step 4, that's going to cause me to reject the null, which it says down here. All right, so let me write up step 6. Here's step 6. It says we can use the p-value method as one way of deciding. So the p-value says 0.0062, and that is less than 0.01, which is my alpha level. So therefore, I can reject the null. So using the p-value method, we reject the null because p, 0.006, is less than 0.01. And if I take 1 minus p, that gives me 99.4% confidence in my decision to reject the null. If I want to use the critical value method, I'm going to have the same result. I'm still going to reject the null because my calculated z-stat is 2.5034 and my critical value is 2.33. So therefore, if I need a significance level of 0.01, we do have enough evidence to reject the null at 99% confidence that the proportion of orders filled correctly is above 90.9%. That's my conclusion at the bottom. Pi is greater than 0.909. The population proportion is greater than 90.9, which means we would want to go with the new process because it does result in better performance in terms of our percentage of orders filled correctly, which is what we wanted to find out about.